Here are a few applications of energy harvesting devices. So the first image here shows a project from the University of Utah. It consists of a fitness monitoring device, and it is powered by the person's body. The second image here is from NC State, and the camera mounted on a pole takes pictures, which gets processed by an on-device CNN, and this estimates drought stress on crops. And this setup is actually powered by a solar panel. The third image here shows a project from the University of Wyoming. In this project, the solar power GPS device is actually attached to these new years, and it is used to study the effects of habitat loss and large-scale natural gas production on the migration patterns of these deers. So, as one can imagine, using a supercapacitor as a power source makes the power source very unpredictable. And power sources can operate multiple times and often interrupt the unit execution of the application. Therefore, these devices come with non-volatile memories or NvMs, so that application data can be preserved across power losses. In addition, the backup process is created in NvM based on the backup policy to ensure forward progress. After a power loss, execution resumes from the most recent backup when the capacitor is fully charged again. This novel paradigm of computing is called intermittent computing. And the issue here is that backups are expensive since they are priced to NvM. Thus, it is important, to maintain the right balance between maintaining forward progress and performing backups, so that optimal use of that harvested energy can be achieved. But doing so is not as easy as it may sound. That's because in intermittent computing, execution must be idempotent to ensure correctness. Idempotency is the property that a sequence of instruction is restartable. That is, when re-executed, it produces the same output every time. Idempotency can be validated in intermittent computing when the first memory access to an address after the last factor is a reading, and that same address has a write after reading that decision. So let me clarify it with the help of the example. In this code snippet, the first access to address A after the most recent backup is a load that reads a value of 0 into register R1. The add instruction that follows increments the value in R1 by 1. Later, a store writes the value 1 in R1 back to address A, and this value gets persisted in NvM. But before a backup could be performed, our power loss happens. And when the capacitor is fully charged, the device wakes up and resumes execution from the most recent backup. But this time, the load will read a value of 1 instead of 0, since address A in NvM holds data value of 1. Afterwards, the add instruction will increment this value in R1, and the following store will store a wrong value of 2 in NvM. So this is an idempotency violation, and it can lead to incorrect program output in these devices. Unfortunately, in order to avoid idempotency violations, intermittent computing systems need to perform extra backups, which can hurt energy efficiency. Prior works have tried to address this issue using different approaches. Broadly, we can classify them into 2 categories: software and hardware-based. The first approach is a task or log-based software technique. The entire application code is divided into atomically durable tasks by the programmer. The updates within a task are stored in log into atomic, and then the log is committed in NvM. And also at the end of the task, and also a backup is performed. The problem with this type of approach is that the programmer is not, if the programmer is not careful enough by defining the task boundaries, task may never finish and get stuck in a non-terminating execution cycle. The second approach uses a hardware mechanism to detect stores that violate NvMR and invokes a backup before persisting the value of the store. And in the image shown here, store A and store C can cause idempotency violations. So in each case, a backup is done first, and the value of the store is persisted after the backup, as shown by the dotted arrow. We believe for better backup flexibility, backups should occur only when there is a dearth of energy or hardware resources, and not because of application characteristics. So this leads to the motivation behind our work. To understand the motivation, let us take a look at an example code. The image here shows the persist orderings that exist between stores of a sample code that is executed with a system on a system with constant power supply. Now, if you run the same program in an intermittent computing device, the execution can be interspersed with many backups. These backups introduce many additional complex persist happens before orderings. And this may be due to either potency and other requirements. Please don't worry about these errors and stay with me here right now. So I'm going to explain a little bit later. So now the crux of the issue here is that it can be a nightmare to enforce these orderings, and even though they're really crucial for practice of the program. Our insight comes from the observation that idempotency requirements stems from a war dependency, and the go-to architectural technique to mitigate all these dependencies in registers is renaming. So we propose the same, but for NvMR addresses. So with renaming, the orderings shown with red arrows are no longer required. For example, this red arrow that is required for idempotency, this gets removed, and let me show you how this gets removed. Suppose this node reads a value of 0 followed by this store that writes a value of 1, which gets persisted in NvMR. And there's a power loss before the next backup. The program will be re-executed from the previous backup when the device breaks up. And this load will read a wrong value of 1 because the value of X holds the value of 1 in NvMR. With renaming, this reordering is no longer required, since the store to address X is persisted in address T. So on the right side, you can see that. In case of an ever power loss, the load after the previous backup will read the correct value now from address K. So, for more details about these persist orderings and how they are removed, please refer to our paper. Based on this insight, we come up with NvMR, a hardware architecture for intermittent computing. NvMR, we only reuse NvMR addresses that violate idempotency. In NvMR, persist orderings are relaxed, and there is a better backup flexibility. Thus, any backup policy can be used depending on the deployment conditions of the device. Let's move on to the next part of the talk and take a closer look at NvMR architecture. So in intermittent computing devices usually have single core architectures, and recent works have shown the benefits of having a volatile data cache in the memory hack. For NvMR, we add an idempotency violation detector that consists of two structures, a local boom filter or LBF and global boom filter or GBF. Both record a type of access to an address after the most recent backup. That is, whether it's a read or a write. LBF stores information for each word in the cache block, and there is an LBF per cache block. And GBF stores information per cache block and be encased across combinations. For renaming, compiler reserves a region in NVM for a map table of trailers and the addresses or mappings that will be used for renaming. Map table stores the most recently backed up mappings, and playlist holds the mappings available for renaming. There's a volatile map table cache also. To understand how NvMR does renaming, consider the dirty cache block, which I highlights here. The first access to this block after the last backup was a read to word C, and followed by a store to word A, which wrote the value A new as shown here. So this cache block has a right after read to word C, and this access information is stored in the LDF for the cache block. During eviction, the LDF is looked up to find if the cache block value is identical. Since in this case it clearly does, it will be marked as an identical by the copy GBR. So this block needs to be renamed before it gets persisted in LDF. The first step of renaming involves a lookup in the map table cache. In case of a hit in the map table cache, the mapping return is used to store the data in the In this case, however, the lookup is a miss, and resulting in a subsequent lookup in the map table in NvMR, and for fetching the most recently vector map. The lookup in the map table also misses, so a new mapping is used from the header request, and a new entry is allocated in the map table cache to store this new mapping. The data from the evicted cache block is written to the address pointed to by the new mapping. So that's how the rename is done. And on the subsequent load list for the same block, the map table cache is looked up before fetching the data from it. The most up-to-date data is fetched using the latest mapping from the map table cache, and the LDF is updated using the information that's in GDF. During backup, the map table cache entries are written into the map table. And since the map table holds the most recently backup mappings of the linear and nonlinear addresses across power losses, execution is always guaranteed to the system. For more details about the architecture, we are interested readers to refer to the paper. Now let's take a quick look at the primary results. We evaluate benchmarks from Miguel and Perais using publicly available power quizzes. We use a cyclic rate simulator based on simulator, which emulates the 16-bit ARM ISCA'. And for energy model and area estimation, we use the resources shown in this slide. The table on the right shows the configuration used for producing the results for NvMR. So this is the first set of results. The first result here shows the percentage of energy savings in NvMR compared to Juan, which is a hardware-based intermittent architecture that detects hydroponics values on the fly, as was discussed previously. We use three backup schemes. The first one is a time-based scheme, which does a backup every 8,000 cycles. With this scheme, NvMR achieves about 90% energy savings. The second one is an annual-based scheme, which consists of a tiny neural network that predicts the time to do a backup just before a power loss. NvMR achieves around 16% energy with this scheme. The third one is an ideal scheme that accurately predicts the time to perform a backup that just before a power loss. And with this scheme, NvMR achieves about 30% energy savings. The key takeaway here is NvMR saves more energy with more sophisticated backup techniques due to a better backup flexibility. However, there is a small overhead of 6% in on-chip area for that map table cache and 6% in NVM memory footprint for the reserved region in NVM. The second result here shows the percentage of energy savings in NVM compared to block-based intermittent architecture called who was actually originally proposed for persistent memory systems. We modified Group to semantically resemble intermittent architectures that maintain store updates in a log and commit them at the backup time. With timer-based and ideal backup schemes, NvMR saves around 19 and 40% energy savings respectively. For further details, please refer to about the results on sensitivity analysis. Please refer to our paper. So in conclusion, intermittent computing devices unnecessarily need to perform backups, extra backups, guarantee correctness, even though there is plenty of energy to fitting execution. Non-volatile renaming is used to decouple the backup policy from the availability constraints imposed by the application. And we propose a hardware solution in NvMR that means only NVM addresses that apply the addresses. In doing so, it achieves around 20 and 40% savings compared to other intelligent computing approaches with a small scope. Thank you.
Thank you very much. Any questions? Please identify yourself before you ask the question.
Sure. Hi, I'm Cebrian from Harvard University. This is very cool work. I was wondering, in the energy response, do you account for the overhead energy of the extra 6% for them to come off? And also the energy overheads for that little neural network or the ML-based heuristic, stuff like that.
You mean energy from the network?
Yeah, the energy it costs to compute when to do backups.
Yeah, so we can consider the energy for the network because this is just for the computing part. That's the short answer for that. And then the second half of the question was, do we consider the energy for the NVM? Yeah, we actually took into consideration the energy for the NVM also. So we use the numbers from a data sheet for a microcontroller code. So we model it based on the microcontroller code. That is what we was using that, and we also use like a analytical model that was done previously in the picture. So using those numbers, we came up with the NVM numbers, and for the Ashkan storage, we also use like that.
Thanks.
Okay, let's thank the speaker again. We're going to the second paper, the motivated test paper award. Can I ask the presenter to jump on the stage here? So the second paper in this session is entitled Free Atomics, Hardware Atomic Operations Without Fences. And this is work done by Ashkan, Asgharzadeh, Juan and Cebrian. These are from the University of Murcia, Spain. Arthur Perais from Centre de la Recherche Scientifique. Sorry for my bad French. And Stefanos Kaxiras from Uppsala University. And finally, Alberto from the University of Murcia. Do we have some people that could help us here with the mic?
So, good morning, everyone. My name is Ashkan from the University of Murcia. I'm going to present a work called Free Atomics, Hardware Atomic Operations Without Fences. Let's start with the motivation. Atomic pre-qualified write instructions are the building blocks of synchronization idioms used by parallel applications. According to the x86 specification, atomic pre-qualified write serialized memory operation, which is realized by surrounding them with fences. However, fences impose huge performance penalties. Therefore, we propose free atomic operations without fences, which enables speculative and concurrent execution of atomic rate modifiers. After removing the fences, free atomics has to guarantee memory ordering across atomic rate modifier rights and also has to prevent deadlock. These are the key contributions of this work. After covering the base motivation, let's see that how atomic rate modifier rights are implemented in ISCA'22 process. As their name implies, they start by reading the data, which happens with the load operation. Then there is an arithmetic or logical operation in between for modification. And finally, they write back the data to the memory, which happens with the store operation. In this example, we are going to cover atomic fetch add instruction as an example. As you can see, the micro operations, there is a fence surrounding the atomic rate modifier. The first fence is responsible to complete all the memory instructions, including draining the store buffer before issuing atomic rate modifier. However, draining a store buffer is too costly performance-wise, and we measured 167 cycles by simulating 32 isolate like cores in general. After draining the store buffer, the load operation, apart from reading the data, has to lock the cache line to guarantee atomicity. This is called cache locking. Cache locking denies memory requests either from the local core or the external core to the locked cache. After reading and performing the modification, the store operation comes in and enters the store buffer. It finds the store buffer empty, and once it performs, it has to unlock the cache line to make it accessible again to the other memory requests. And finally, the second fence, once it commits and leaves the reorder buffer, the younger memory instructions are allowed to be issued. The latency of atomic operation itself is measured around 36 cycles in ISCA codes. So now let's start to discuss about our proposal, free atomics. In this section, we also cover evaluation as well. Free atomics are built on 3 steps. First, speculative execution of atomic rate modifier rights, then removing fences or unfencing, and the last step is enabling the store to load forwarding atomic rate modifiers. Finally, we show that how all these 3 steps can be implemented in hardware through atomic Q. The first step is speculative execution. Atomic rate modifier rights can execute speculatively with the presence of fences, while it is not mentioned in the documentation. But it can impose the threat of a squash to atomic rate modifier rights. The squashing can be considered as a challenge because it is possible that the atomic rate modifier right has already locked the cache line speculatively. In this case, the atomic rate modifier right, the atomic has to release the locked cache line once it is squashed. Here we show the performance result of the speculative execution of atomic rate modifier rights with the presence of fences. The performance improvement is limited, but speculative execution is necessary to enable free atomics to get benefit from unfencing. Here in this performance graph, we show only the results for atomic in-fencing applications by measuring, by simulating 32 isotopes in general. The second step is removing the fences, which we call it unfencing. After unfencing, the macro operations of atomic rate modifier are shrunk to just the load, the store, and the arithmetic or logical operation bit. After this step, we start calling the atomic rate modifier free atomic. Unfencing is a significant step for free atomics, but it brings some challenges that free atomics has to deal with them to make its proposal feasible. The first step is to enforce the storable order across atomic rate modifiers. This is necessary because in TSO memory model, all the memory orderings are preserved except the store load order. Also, TSO memory model expects that the load and store operation of the atomic rate modifier has to perform atomically. So to enforce the store load order, free atomics has to commit after draining the store buffer, but still they are allowed to execute speculatively, which was not possible in the first implementation. The second challenge is that after removing fences, now multiple free atomics can execute concurrently. So it implies that the hardware must support multiple lock caches. Our solution to manage this is an hardware structure that we call it atomic cube that we will see later. The third challenge that I'm going to discuss here is the appearance of deadlocks. Deadlocks can happen after removing the fences because atomic rate modifiers relies on cache locking. In the paper, you can find many possible deadlock scenarios that we discussed, but here we just rely on one example. Imagine that in two different cores, the younger free atomics execute speculatively first and lock cache line A and B. Then the older free atomics at the head of the reorder buffer, they try to access the cache line, but since it has been already locked, they have to wait. This can end in a deadlock because the older free atomics cannot commit and leave the reorder buffer, which causes the younger free atomic cannot commit neither to unlock the cache line. To prevent this deadlock and any other possible deadlocks, we propose to squash the oldest executed free atomic, which here means the younger one, which has already executed but not committed, based on a watchdog mechanism. So once we squash the younger free atomics, then the older free atomics can access the cache line later, and finally they can commit and leave the reorder buffer and let the system to progress. This solution is generic and can prevent any possible deadlocks that can happen either due to reordering memory instructions or due to limited resources in hardware. Also, our solution doesn't require any changes in cache coherence protocols nor checkpointing. Also, we do not broadcast any messages, and also we do not degrade atomicity semantics. We observe that the timeout mechanism triggers even rarely even in 32-core simulation. After unfencing, free atomics can achieve 24% performance improvement for atomic intensive applications. Regarding unfencing, you can find more in the paper, like how we treat local memory requests and how do we prevent live loss, for example, due to replacements. The last step of building free atomics is enabling a store-to-load forwarding, which is realized by concurrent execution of multiple free atomics. So now a free atomic can search a store queue for a match. And if it finds a match, it reads the data through a store-to-load forward, and the request to the L1 data cache will be discarded. So this can cause a challenge because how we are going to guarantee atomicity. To guarantee atomicity, we propose that the forwarding store locks the cache line on behalf of the forwarded free atomic. So it means once the forwarding store leaves the store buffer, it has to lock the cache line that we delegated this responsibility to the forwarding store. And later, once the store operation of the free atomic performs, it will unlock the cache line as its usual responsibility, and the cache line will become accessible again to the other memory requests. The results of store-to-load forwarding can achieve up to 5% additional performance improvement over free atomics. Now let's see that how free atomics are implemented in hardware. We propose atomic Q, which is a FIFO that realizes hardware implementation of free atomics. Each entry of atomic Q belongs to a different free atomic that is allocated once an atomic grid modifier is dispatched. Then later, once the load operation of atomic grid modifier executes, the log bit in the corresponding entry has to be set to indicate that the cache is locked. And the log bit and the L1D set rate address bit are used to start any memory request coming from external ports asking for the locked cache. And finally, once the store operation performs and leaves the store buffer, the corresponding entry is released, which means unlocking the cache. Regarding other fields, sequence number is used either for rescheduling free atomics or for dispatching free atomics. The store queue ID provides the support of store to load forwarding. One of the elegant features of the atomic queue is that flushing it is as straightforward as flushing the reorder buffer. And based on our sensitivity analysis, we observe that 4 entries is enough for the evaluated applications to provide required concurrence, which leads to a small area overhead around 15 bytes in isolated ports. Since we covered, I showed the evaluation in the proposal, in the description of the proposal. Now I will conclude the talk. 3 atomic omit fences of x86 atomic grid modifier. We propose atomic Q, which realizes the hardware implementation of speculative and concurrent execution of multiple free atomics. And the impact is that we improve performance by 25% for atomic intensive applications, and proportional to performance improvement, energy is reduced by 23% for atomic intensive applications, which is mostly achieved by reducing static energy.
Let's start speaking.
Yeah, this is Frank from Future Technologies. How do you compare your proposal with log collision and transaction memory? Log collision and transaction memory. How do you compare this?
Quantitatively, we didn't compare the proposal, but so there are 2 ways to implement atomic grid modifiers in hardware. Either you want to rely on cache locking to guarantee atomicity, or you can act like loading a store conditional to let the atomic grid modifier be expressed speculatively. So the focus of this work was to improve the performance of atomic grid modifiers, the ones that are reliant on cache locking. So I would say that working on loading and store condition could be considered another work. Yeah, but quantitatively didn't do the comparison. We just talked about the related works in the last section of the paper. Like there was a proposal called fast grid modifier rights that they proposed 2 different atomicity semantics by degrading the atomicity. But here, free atomics do not degrade atomicity. We just let the atomic grid modifiers to execute speculatively to gain performance. Thank you.
Unfortunately, we will have to move on here because we're behind schedule. So let me ask first, let's thank the speaker. Stage, and also the last 2 papers, the presenters of those, please come to the front row so we can save some time. Okay. Okay, so while the third presenter is getting ready, let me introduce the paper. It's entitled "Securing GPU with via region-based bounce checking, and authors of that paper is Jaewon Lee, Yonghae Kim, Jiashen Euna Kim from Georgia Institute of Technology, Bhattacharyya from Alt Research, and Hyesoon Kim from Georgia Institute of Technology. Jaewon, please take it away.
Yeah, good morning everyone, and thank you for this introduction. Hi everyone, thank you for attending my presentation. Today I will present the securing GPU via region-based bounce checking. Security threats are serious problems, and the major security threats comes from the memory safety problem. According to the studies from NS and Google, about 70% of all the security bugs are memory issues. Then, first, you need to know what is the memory safety. Memory safety is providing protection against the security vulnerability and software bugs when handling memory accesses. Well-known memory safety problem is buffer overflow. Let's think about locating two adjacent buffer A and B. Then let's trigger buffer overflow on A. Now access to B will return the overwritten value instead of B's original value. With the buffer overflow attacker could get root access and have unlimited access to the system resources. Yeah, root access. So it sounds like it is related with the CPU, not the GPU. That's the reason CPU memory safety has been studied for a very long time, but not much done for GPUs. Because GPUs are considered reliable or unharmful for GPUs work on important data. However, concern about GPUs memory safety arise because GPUs handle private and secure information like machine learning training for medical images. And recent mind control attack demonstrate the GPU buffer overflow to interrupt other GPU's application running on the cloud servers. Before talking about GPU memory safety schemes, let's check out CPU solution first. There are various memory protection schemes for CPUs, but let's focus on the hardware bounce checking mechanism here. Basically, bounce checking mechanism is triggered by memory accesses, and it checks whether access memory address is within bounds. Buffer ID is a unique descriptor for each buffer, and it is embedded in the unused upper memory address bits. Bounds table maintain the information about each buffer, such as buffer ID, address, and size. And actual bounce checking mechanism starts when actual memory access occurs with a low storage instruction. Then, if we just apply this into GPU, does it work well? Yeah, I don't think so. There are two challenges when you consider optimal GPU solution. First one is the no register extension, and second is the no bandwidth increase. GPUs adopt massively parallel execution model, so total resources are required by system are multiplied by number of threads and number of blocks and number of SMs. It means that even we just need a 2 register and one memory request are used in one thread, that will multiply by 32 in a work level, and it will be multiplied by 128 in SM level. Obviously, this will introduce a severe overhead without proper optimization. So now we have discussed what memory safety problem is and why it becomes serious in GPU type. Now let's move on to the GPU program observation. First observation is that all globally visible memory buffers used by a GPU kernel must be specified in the kernel argument. Kernel argument size is limited by programming specification, so the number of buffers in GPU is limited too. Moreover, we investigate the number of buffers in 148 applications, and the average number of buffers in the application is only 6.5. As a result, GPU kernel maintain only small number of kernel buffers during its execution time, and we keep track of these buffers for protection. Next observation is there are three types of GPU addressing methods. Method A is using binding table for subset. Binding table is usually used for graphics objects like sortings or texture. It contains the information about memory objects such as size. Method B is full virtual address, which is normally used with the CPU program. For method A and C, we know this. Method C is base plus offset, and base is usually kernel buffer address. So size is determined before the kernel launch time. For method A and C, we know the size of the memory object, so we will show how we'll utilize it for the EG bound shaping. Let's see how we should work along with the GPU program procedure. At time, host code and kernel code are analyzed with LLVM to filter out the memory access, which can be validated at same time. And we also categorize the point code. We also categorize the point type for further optimization. This information is stored in the bound analysis table, and this will be embedded in the GPU library. When GPU program starts, GPU driver generates encrypted buffer ID and embedded it into the pointers. GPU driver also creates a region bound table with bound analysis table and store it into the GPU memory. At runtime, hardware bound checking mechanism utilize a region bound table to do actual bound checking. Now let's take a look at a simple example of our static analysis. The purpose of our static analysis is to detect the statically known memory addresses and filter them out. To do so, we first gather information about kernel buffer, location, and the number of threads in the host code. And then we move on to the device code and search for the memory address instruction, which address is calculated using static values. For example, the indexing A of TI plus offset is calculated by adding the thread ID and the static offset value. Since we know the maximum number of threads, and we can calculate the maximum index value as 136. And since it is less than the size of a buffer, so that we consider the memory instruction to be safe. Unlike the previous example, P of TI plus D contains the variable given by user D. It should be verified at the runtime. From the static analysis, GPU should determine whether a given pointer requires runtime check or not. And this decision will be embedded into the unused upper memory address D by GPU driver. As we discussed in the previous slide, A of Ti plus offset becomes type 1, which means a low protection. And B of Ti plus D needs to be checked at runtime. So this becomes type 2, which has encrypted buffer IE on the upper bits. As this memory access generates multiple unclosed memory requests time, GPU should only collect the min-max address of all of them and compare it with the bounce information in add-on and element cache, even in the memory. The last pointer type for the method is for the method A and C, which can utilize size information before kernel launch. In this case, GPU should embed the buffer size to the upper bits directly. So they can do bound checking without accessing all bit table. Okay, so let's look at our experimental setup. We target the two GPU platforms, NVIDIA GPU and Intel integrated GPU. We do experiments of L1, L2 latency sweeping and check the impact of static analysis. Vertical integration and comparison with an existing software solution are not covered here. So please refer our papers. And we evaluate our system on maximum heterogeneous microarchitecture simulator. Yeah, here is the overall result. GPU shield shows a near zero performance overhead on various benchmark categories. Main reason is that the most benchmark exhibit very high add-on RPS hit rate because of the small number of kernel buffers in GPU applications. Even when we increase the cache latency to check the latency sensitivity, we observed negligible overhead for most applications. But it is shown that the thread level parallelism in GPUs can tolerate the penalty to some degree. But however, the string cluster in the VM category showed a prominent performance degradation since it has a massive number of memory requests. The prominent overhead on the memory central application, like a string cluster, is mitigated by static analysis. As we can see in the red circle, string cluster overhead reduced to nearly zero level after applying the static analysis. And red coloring cases exhibit that only small percentage of static filtering, but it is still help to reduce the overhead. In conclusion, GPU shield is the first hardware uncheck mechanism fully utilizing GPU program property to mitigate the overhead from the massive parallel execution. We use the state time analysis and the embedded integrated buffer ID in unused bit pointers and coalescing against the bound table. GPU still incurs the negligible overhead compared to the existing GPU's memory protected solution with a small hardware overhead. Yeah, thank you.
Any question? Hello, my name is Nominees from University and I have a question that your distribution is still evaluating the multiple situation when you analyze multi-instance GPU that squeeze each memory resources into the component.
Actually, in our in the multi-kernel situation, there are lots of there are many threads that access to the memory, the readable table. But the thing is that we just do it with the multi-kernel simulation, and actually the percentage of error cache this radar is not degraded. So it just shows the high performance as with just a single common cases. So, yeah, it's
Thank you very much.
thank you.
Thank you very much. Okay, so let's move on to the fourth presentation here in this session. It's entitled Jaekyu, polymorphic cache hierarchy for general purpose optimization of data movement. And the authors are Brian Schwedblock, Pirata Govitia, from Carnegie Mellon University, Jennifer Saber from Binghamton University, and finally Nathan Beckman from Stanford. Let me introduce the speaker. Brian is a fifth-year PhD student in the Electrical and Computer Engineering department at Carnegie Mellon University, and he's advised by Nathan Beckman. He works on programmable memory hierarchies that let software primarily reduce data movement. So Brian, do you think you may?
Thank you. Okay, cool. All right, hi everyone. My name is Brian Schwab, and I'm going to talk about how to build a general purpose architecture that enables a wide range of data movement optimizations in software on a single hardware platform. This work was done with Carnegie Mellon in collaboration with my advisor, Nathan Beckman, and undergraduate students, Perais, Yonghae, and Jennifer. Our work is motivated by the increasing cost of data. Computer systems have evolved significantly over time, from cores directly accessing memory to complex multi-level distributed memory hierarchies. This has made data movement increasingly expensive. This graph plots energy and log scale for an arithmetic operation and different types of data. As you can see, data movement is orders of magnitude more expensive than compute, and the trend is only worsening over time. Of course, we're not the first people to realize this. There are literally more than 100 recent proposals for specialized memory hierarchies, recent architecture conferences, including graph optimizations, non-uniform cache architectures, and pointer chasing accelerators, just to name a few. Clearly, there's a big opportunity here because these optimizations often give more than 2x speedup, but there is a huge problem. Each of these optimizations requires having their own custom hardware, which is disruptive across the system step and prohibitively expensive due to hardware design verification costs. Realistically, systems are just not going to have dozens of specialized ASICs in the memory hierarchy. This is a huge lost opportunity, though, because systems do not realize these potential gains. That leads us to the motivating question for this work. How can we specialize the memory hierarchy without requiring custom hardware for each new optimization? Fundamentally, we realize that the problem is the memory interface, and for recent prior work is forced to use custom hardware. On current systems, software can only perform loads and stores, which is fine for older systems with direct memory access, but as we already saw, systems are now much more complex with distributed multi-level cache hierarchies. Yet we still use the same load store interface. Hence, prior designs were forced to add custom hardware within the hierarchy to optimize data movement, because the memory interface gave them no other choice. The thesis behind our system is that the increasing importance of data movement motivates an increasing need to expose data movement to software. So optimizations that previously required specialized hardware can now run entirely in software on a single general purpose platform. Taco achieves this by adding general purpose engines that run software within the hierarchy, eliminating the need for new hardware for each new optimization. We call this a polymorphic cache hierarchy, because it lets software change the functionality of the hierarchy to match the application's needs. Taco gives a practical path to memory hierarchy specialization so that software can directly address the growing cost of data. Taco's key mechanism is that hardware notifies software when data moves and lets software intervene by observing and modifying the data. With Taco, loads and stores work normally for most data. But Taco adds this new notion of fancy data, which is data that lives only within the cache. When the core loads fancy data, an on-this software callback is invoked on the engine to fill in the fancy data. Subsequent accesses to data hit in the cache like normal. And when phantom data is evicted from the cache, Either an on eviction or on write-back callback is invoked, depending on whether the data is dirty. These callbacks let software operate on data as it moves, which we found is a common pattern needed by prior specialized hierarchies that is not supported on current systems. In particular, prior near data computing designs do not provide this capability. They merely offload compute from cores closer to data. This might reduce data movement, but does not enable the kinds of optimization we see in prior specialized hierarchies. Instead, Taco takes inspiration from work done in the 90s on programmable memory hierarchies, which exposed more data into software. However, those systems were responding to the trend towards multi-processing and focused on optimizing the coherence protocol to improve the performance of loads and stores. In contrast, Taco is responding to the trend towards hardware specialization and is designed to implement entirely new semantics in the cache hierarchy. In Taco, caches trigger software, not cores. Intercepting cache misses and evictions is the critical mechanism that lets software observe and control data, which is missing from prior systems. That wraps up our intro to Taco. Now we will go over a quick motivating example. Then I'll describe Taco's design and present a few more results. We're going to start with a simple example that shows Taco callbacks in action and introduces its main components. This example focuses on a lossy compression scheme where an object is constructed from a base and a delta. And unlike conventional base plus delta scheme, values are approximate of the originals. Lossy compression schemes are attractive because they can increase compression ratio. Now let's talk about different ways one might implement this compression scheme. On current systems, if an application wants to access the decompressed data, it needs to load the compressed data from memory into the core and then perform the decompression there. The benefit of compression here is reduced memory and cache use, since only the compressed data is stored. However, if there's temporal reuse on the data, the core needs to repeatedly decompress the same data, wasting time and energy. So what about hardware compressed caches? They decompress data within the cache hierarchy so that higher levels of cache contain the decompressed data. This allows applications to benefit from temporal locality by keeping decompressed data only in the private cache. Unfortunately, not only is the compression scheme fixed in hardware, but hardware-only compressed caches just cannot support loss of compression. This is because hardware doesn't know which data can tolerate approximation. Now let's look at Taco. Here, the application loads phantom data corresponding to the decompressed data it wants to access. When it loads a phantom data misses in the private cache, Taco invokes an on-miss callback in software to decompress the data and store it in the private cache. Unlike hardware compressed caches, the application tells Taco exactly which data can tolerate loss of compression, and other data is not affected. And since the callbacks are in software, any compression scheme can be implemented without requiring new hardware for each one. Let's see how Taco performs on this example. We evaluate an application which computes an average over an array of compressed data, which is accessed using a skewed Zipf distribution. The baseline decompresses data at the core on each axis. The first graph shows the number of decompressions performed, the second graph shows relative speedup, and the last graph shows relative energy. We first evaluate a near data computing version, which offloads decompressions to the L2 cache. It actually performs worse than the baseline because decompressing data at the L2 loses locality provided by the L1. In contrast, Taco achieves significant speed up and energy savings by decompressing data only once when there's a cache miss. Caches then capture reuse of popular data to avoid decompressing the same data repeatedly. Finally, we compare Taco with a version of Taco with an ideal engine that has infinite compute. Taco is close to ideal because performance is not for raw compute. It's about using data movement to know when to compute. Popping up a level now, Taco provides these benefits by triggering compute in response to data. As we saw in the decompression example, simply offloading compute into the memory hierarchy, like in prior near data computing designs, does not provide the same functionality. Taco provides this missing mechanism. By opening up the cache hierarchy software, Taco enables a wide range of optimizations using a single general purpose architecture. Now that we've motivated the need for expanding the memory interface, let's see how Taco achieves this. Taco's two main components are the programming interface and the architecture. Taco's programming interface is currently designed for expert programmers and consists primarily of 3 callbacks. The on-miss callback builds in a phantom cache line when it is first accessed, as we saw in the decompression example. On-miss and on-eviction handle the eviction of clean and dirty data respectively. And that's basically it. We found that these three callbacks here cover a wide range of different optimizations. An application uses Taco by creating what we call a morph. A morph is a data type which implements the three callbacks. Programmers write a morph subclass, then call a register method with the morph, the cache level to execute the callbacks out of the L2 and the LC, and the size of the phantom address range to allocate. Multiple instances of the same morph type can be registered at the same time, but on distinct addresses. An application may also register different types of morphs, but still needs to be on distinct addresses. That covers Taco's programming interface. So now in this next section, we'll look at Taco's hardware. Taco starts with a baseline multi-core processor. On each tile, Taco adds an engine to execute the callbacks. The engine's main components are a hardware scheduler and a data flow fabric. The scheduler spawns threads entirely in hardware without going through the operating system, and the data flow fabric runs the callbacks. To see how Taco works, let's walk through how Taco executes an anonymous callback on phantom data registered at the L3. A core loads phantom address A, which this is in the L3. The cache controller checks that the address is registered with Taco, so it spawns a thread to run the callback. On this, then fills in the data, which is returned to the core when the callback ends. Subsequent loads to address A, hit the L1 like normal. And when data is evicted from the L3 cache, Taco will similarly execute an on-the-write-back callback. The tags indicate that the address is registered, so after child caches are invalidated, the controller invokes on-write-back on the data. Once the callback completes, the data is evicted from the cache. That covers the typical life cycle of a phantom cache. Taco adds a small amount of state to track which lines have callbacks registered and to perform address translation. This adds less than 3% state compared to the L3 cache. Our data flow fabric is similar to many prior data flow designs. It's an array of simple processing elements that uses dynamic data flow firing to issue operations when their inputs are available. Overall, the fabric has approximately 3% area compared to the L3 cache. We found that data flow fabrics are a good fit for Taco for a few reasons. First, the most important is that callbacks need memory level parallelism to perform well, which data flow engines provide, unlike inner cores, which have been used in some prior data computing designs. Second, Taco callbacks tend to be short, so they easily fit on a small fabric, overcoming one of the main limitations of data flow architectures. And there are several more reasons discussed in the paper. But in general, we found that data flow engines tend to work very well for Taco. In particular, provide a 3x end-to-end speedup compared to an inner core, due largely to memory level parallelism. That wraps up Taco's design. Now, we'll demonstrate the full potential of a polymorphic cache hierarchy through more case studies. We evaluate Taco in cycle accurate simulation. Our system consists of 16 tiles, each with an allegory core and a Taco memory. In total, we evaluate 5 different case studies, but I only have time to go to 3 for this talk before showing. And we already looked at the decompression study, so we're going to look at 2 more now. Starting with an example that redefines the cache to exhibit push semantics, and finishing with an example that detects cache-side channel text. Our next example shows how Taco can fundamentally change how the memory hierarchy behaves. Graph algorithms exhibit a common pattern called scatter updates, where each section needs to update all its outgoing neighbors. Unfortunately, cache hierarchies are very bad at scatter updates due to the pool-based nature of current caches, which bring in data from lower levels when there's a cache miss, leading to wasted bandwidth and extra synchronization. Phi is a previously proposed specialized hierarchy that changes the memory hierarchy from pool-based semantics to push-based. When a core updates data, instead of loading data from memory, Phi buffers the update in the cache. Subsequent updates coalesce to the cache. And updates are only applied when evicted. Finally, the number of buffered updates in the cache, depending on the number of buffered updates in the cache line, the updates are either applied directly to the data or along for later processing, which improves spatial locality. Phi is very easy to implement with Taco's callbacks. An application starts by registering a morph of the L3 cache for the vertex data. On a cache miss, on-miss provides a zeroed-out cache line. Subsequent updates are simply written to buffer phantom cache lines. When a line is evicted, on-write-back checks the content of the line to decide whether to apply the updates in place or to log them for later. using the same logic as phi. So we now implement the semantics and software without requiring custom hardware. And importantly, this is not possible without Taco, since software cannot respond to cache insertions and evictions only using loads and stores. The Taco version of phi replicates the conclusions shown in the original phi paper. First graph here shows normalized memory accesses, second graph shows speedup, and the last graph shows energy. The software baseline always applies updates in place. Alternatively, we have a software implementation that always logs updates. Logging reduces memory accesses and gets some speedup. Then we have Taco, which decides dynamically whether to apply updates in place or log them, and I'll be right back, reducing memory accesses further to achieve even better speedup. And further, Taco is close to ideal because, as with the decompression example, compute is not the bottleneck. Our final case study focuses on a different aspect of Taco's benefits entirely. It shows how providing an application full visibility into the cache hierarchy, for example, where a state is located, can provide entirely new features beyond just performance and energy efficiency. This case study shows how applications can detect the common prime and probe cache side channel attack with Taco. I'll start by demonstrating how the prime and probe attack works. The threat model is an attacker trying to detect when a victim accesses a target cache set. Initially, the victim loads some of its sensitive data into the cache. The attacker starts by priming the cache set with garbage data, which evicts the victim's data and is importantly invisible to the victim on current systems. The attacker then waits for the victim to access the sensitive data. Finally, the attacker probes its data and checks how long its load takes. If any access misses memory, the long latency informs the attacker of an access to the target set, leaking sensitive information. Taco can detect and interrupt these kinds of attacks by notifying the victim when the attacker primes the cache before any sensitive data is leaked. Let's see how the prime and probe attack looks in practice. This graph shows a trace of evictions from different sets of a shared cache vector. The victim performs an AES encryption and currents some evictions. The attacker then primes the target set, evicting the victim's data. The next encryption by the victim evicts the attacker's primed data, which leaks sensitive information. So when the attacker probes the set, they detect an attack from the victim, extracting information about the AES key. Now let's look at the same cache eviction trace for Taco. Once again, the victim performs an AES encryption. However, this time, when the attacker primes the cache set, on eviction is triggered, detecting the attack before any data can be leaked from probing. This example demonstrates an entirely different class of benefits from the other case studies. Instead of optimizing for performance, this application uses Taco to gain visibility into the cache hierarchy. Such feedback from hardware to software is simply not possible with the traditional memory interface. I'm going to show the subset of case studies evaluated in the paper, so please check the paper for more interesting examples using Taco as well as some such case studies. To wrap up, we've seen that the current memory interface severely limits application performance and functionality as data movement becomes increasingly expensive. A wide range of specialized hierarchies try to circumvent this issue by incorporating custom hardware, but that's not a practical solution. Taco addresses the issue head on by opening the cache hierarchy to software, enabling new optimizations that are impossible on current systems. Thank you.
Present the black paper to get ready for presentation. And we unfortunately only have time for one question.
I have one question on the area overhead. As far as I understand, the Taco engine is updated with each port, right?
There's one top which is per tile.
Yeah, per tile. You said it's 3% of the area overhead over a LLC over the L3 cache. So it means maybe 50% of the whole chip.
No, it's 3%. One engine is 3% area of a single LLC cache thing.
Okay.
So it's all the engines combined is 3% area compared to all of the LLC things combined. Okay.
And another question is, what's your granularity of accessing data in Scala, vector, or strings?
I'm sorry, can you repeat the question?
I mean, what's your granularity of accessing data in Scala, vector, or strings? I mean, include the memory index.
I'm sorry, it's very hard to hear the question right now. Should I is your question what was the overhead of accessing data?
Yeah, I mean, how many instructions are requested?
Oh, all background instructions each one day.
The memory access instructions, how many instructions and how many type of program?
Oh, how many memory are they structured by the whole program? It totally depends on the program. With graph applications for that case, it'll be, general Dutch talk would be something like you have to access all of the edge data at least once, and then the vertex data. And for each single update, you have to access whichever cache line of the vertex data. For each application, it's totally the application. Thank you.
Okay, it's time for the speaker. Session. It's titled EQC, Ensemble Quantum Computing for Variational Quantum Algorithms. And it's written by Samuel Alexander, Nathan Weaver, Yufei Kim, Ken Liu, Carol Kowalski, Nathan Baker, James Ang, and all of the authors are from Pacific Northwest National Lab, except for Yufei Kim and UC Santa Barbara. Please. Thank you.
People can hear me. Cool. So hi, I'm Samuel Stein. I'm going to be presenting our work on distributed quantum computing, titled EQC, Ensemble Quantum Computing for Variational Quantum Algorithms. This is written by us at PNNL in partnership with the University of California, Santa Barbara. So, to kind of set the scene, I'm going to motivate why we care about variational quantum algorithms, what's the current sort of limiting factors, and what are the real problems we're running into when trying to train these large systems. So, to begin with, variational quantum algorithms are considered one of the most promising algorithms in the noisy intermediate scale quantum era, the NISQ era. These algorithms have applications in a wide range of domains. Specifically, some of these, for example, are quantum chemistry for drug synthesis, minimum energies, minimum bond energies, quantum optimization problems, that's doing things such as partitioning graphs into two subsets, quantum machine learning, similar to classical machine learning, doing things such as classifications, such as data synthesis, mostly motivated on data such as quantum data. But what really matters is these all fall under one large corpus, and that is they all are trying to do that characteristic thing where they're trying to find a set of parameters that they can apply to some function over some quantum circuit that's going to minimize, that we're going to minimize this function or maximize, depends on what you do. And so some of us don't really know that much about quantum computing, but at a high level, the circuit on the right is the generic structure of any variational quantum circuit at a really high level. Quantum computers, the way we run them, are circuits. Each line is a bit, quantum bit, and exhibit superposition and can be entangled with other qubits. But hopefully that's as a single quantum computing. But for variational quantum circuits, what they have is they have this three-step kind of procedure where you begin by preparing your superposition into maybe an initial guess, a data point, similar to classical machine learning. Moving on, then you have a parameterized transformation. That's where you manipulate your data by some parameters. This can comprise multiple gates, multiple operations. But what matters is that bank, that used data, that's some unitary, comprised of lots of operations, and at least one of those operations must be parameterized. Finally, you move on to measurements. Measurement can get a bit complex, but all that matters is you're measuring in some way. You're observing some observable. To give a concrete example, I think that it can get a little confusing, a little lost in that. Let's just run through one. So here's an example of variational quantum circuit. It's a 4-qubit trainable circuit. This is called efficient SU2 in qubits. It's a linear entanglement. That's the yellow box. So to start out with, we begin with our fiduciary states. That's the zero line at the left. We don't have any trial state preparation. And so what that means is right now, there's a 2 to the 4 vector representing just 16 values, which is the superposition. We then move into that unitary section where we have all these rotation gates, and what these are matrices that change your state by some theta. I mean, so you have these 16 matrices right here. These are 16 independent thetas that you're learning, similar to weights in neural networks. And those yellow blocks, those don't have parameters. They're fixed matrices. They're actually full matrices, and they create entanglement, right? Teleportation. And then you move on and you observe in some way. This observation, with quantum computing, the beauty is you can also observe in different dimensions. You can transform and observe the x-axis or the z-axis. But what matters is you're doing some observation. You might not be observing all, but you are observing some subset of this. On the right, we have this argument theta psi h plus stuff. But basically, that's just going to print out a value. And that value is what you're trying to optimize towards. You're trying to minimize that value. And that's 5, that's the output state. So that's going to be 2 to the 4 values. And then h is a 2, and it's a 16 by 16 matrix. And when you do that matrix multiplication, you just get a number. And as a simple example, if you have a Hamiltonian which describes the energy of your system that you're trying to find the minimum eigenvalue of, you would want to minimize the coefficient. You would want to find the state vector that presents the lowest energy when you do that cost function. And in this simple Hamiltonian, if you had only a -4 at the 1, 1 index of your matrix, what's going to happen is you're going to stop all these states, they're going to be flying around, and they're all going to want to maximize the probability coefficient to the -4. And so they're going to drive you to the ground state being complete 0 states. That's very from quantum studies. It's actually pretty intuitive. The problem with quantum computing though is, accessing gradients is not that easy. Quantum computers, you cannot observe them, you can't directly get the state vector, you do estimations, all that stuff. So computing gradients is actually really challenging. And the way you do that is through the parameterized difference method. And one thing that should jump out immediately from this is that's really expensive. That's 2 circuit inductions for 1 gradient. So for this kind of small-ish circuit, we have 16 parameters. To train 16 to get 1 iteration of parameters, we need 32 circuits. So we need 32 circuits, and that's a lot. How long is that though? So we're in this era, that's the noisy intermediate scale quantum era. And the way currently we operate is that are provided with quantum computers. And you need to submit and join a queue and try and wait for your job to run. And if you submit this job independent, 1 circuit at a time to, for example, Perais ISCA'22 NvMR on a 5-qubit system, and you submit and you wait approximately 2 minutes per wait, which is pretty good. It's sometimes it's like a full day. And you try and train the circuit for 100 iterations, you have around 16 days to train the circuit. And that's assuming you converge. There are much more complex ansatz is the structure of your circuit that have many more parameters, many more qubits that you need to optimize over. So right on the left, we've got it's really difficult. The computational cost is up there. But there's actually a really interesting other thing that is that every quantum processor is different. And every quantum processor exhibits these temporal kind of dependencies, when will it last calibrated. So I'm going to kind of just go through these 3 here, where there's topological constraints. What this means is data qubits can only interact with qubits that are on their nearest name, or that they are connected to. That puts constraints on your circuit construction, and we can override it by using swap gates. However, that is at the cost of errors. Time-dependent drift. As days goes on, cosmic rays hit these quantum processes. They get a little weird. They get a little less as the day goes on. And calibration happens for IBM, for example, once per day. And this kind of resets it to a benchline baseline. And we kind of get more intuition and we get statistics about their performance. But that kind of degrades as the day goes on. And the quantum processor quality, similar to classical computing, there's just how good is this quantum processor? You can't tune it to be perfect. You need to make it as good as you can in the beginning and then kind of maintain it. And so we have these rotations, right, these parameters that we were learning. And this is an example of where you would have this temporal problem, where on the left we have IBM NvMR. This is a real machine statistic. This was pulled, I think, December last year-ish. And we have qubit 4 having a T1 time of 10 microseconds. This is T1 times of the ability to hold information. And this T1 time is 10 microseconds. Then we look at Santiago and it has a T1 time on qubit 4 around 100 microseconds. So if you're starting to learn these parameters that is trying to compensate for this noise model, what you're going to exhibit is suddenly Lima is going to start to overshoot its rotations to try and kind of overexcite the quantum state to make it such that it's going to degrade probably, but it's kind of overcompensating that. Say you have a neural network right on a quantum system. You move 5 into Santiago, your parameters are useless. Your accuracies are now half of what they were. And so, that's the problem of calibration. And then it's just like this high-level problem of quantum processes that we exhibit right now. And this crosstalk, which is similar to classical Euler, is this interference on operations. So when you have highly connected qubits, what happens is you pulse them, kind of, there's a mixture with the bar, and gets a little, not ideal operations, kind of, is what happens. And then there's also, so what you can do to minimize that is minimize the connections that you have per qubit. But then you can have low qubit incident connectivity, and suddenly if I need data to commute across my entire system, I need to move things around, and that's the cost of swap gates, and those are very erroneous. So it's kind of like a catch-22. You want to have high connections, but it makes errors. So now what we've set the scene is like right now on the left is it's really computationally expensive. Secondly, you need there's no generic design. When you run parameters, you're running them for that moment. And this is really this is really bottlenecking current variational quantum algorithm performance. So what we motivated is EQC to kind of tackle these two for training these algorithms on real machines. So EQC, ensemble quantum computing, is a single master node, multi-client node distributed optimization system. It optimizes using asynchronous stochastic gradient descent and has three key contributions to this field. One, we provide substantial fidelity boosting for variational quantum algorithms and kind of generic machine learning, where we're able to learn parameters that are generic to quantum computers through the notion of kind of similar to boosting, where we have this mixture and we kind of wash away this machine bias. Secondly, we observe substantial training speedups. Substantial training speedups, and naturally we're distributing, things are going pretty quick. And finally, we also generate this missed error weighting model where we're able to kind of rank quantum processes and their reliability for exact circuits. So prior we have quantum volume, which kind of is like the high level maximum capability of the system. But we've created this model that takes a circuit and a backend and gives you a rank kind of like, this is good, bad, medium, and sequences them accordingly. So side note, now we're on asynchronous stochastic gradient descent. We're not using parameters from time t to update t+1. We're doing tau, which is sometime in the future of t. And as long as tau minus t is bounded, then you have enough iterations, you are still guaranteed to converge. We further read that to our paper, which we devised to another paper for that group. So here's EQC, and I'm going to run through this to gain intuition as to how we use EQC and what the user kind of interacts with and what it does. So we begin. The user provides a variational quantum circuit comprised of a circuit and a loss function and kind of just the general start of a variational quantum algorithm. We move on, we submit that to EQC. EQC paints all providers available to it that you have given it aware of. If you want superconducting, trapped ion, free atom quantum computers, it'll connect to all of them. It'll initialize that many client nodes as it has quantum computers. And those client nodes are now ready, waiting for jobs. Every client node connects to one independent machine. They share no information. The master node then initializes the parameters, and starts to create jobs. And those jobs are optimization jobs. The client nodes then consume these jobs linearly and at each iteration. The client nodes then go off, they transpile their topology, they compute a weighting model, a ranking model, and they send it off to the quantum processor. The quantum processor then runs the circuit, it computes the relevant information, and it gets sent back to the client node. The client node consumes this information, transforms it into the desired information from the master node, and the master node then receives this. The master node then sees how well it thinks it did. The client node doesn't know how well everyone else is doing, and the gradient. And the master node will take this in, update its parameter, and then be like, great, we have another job for you. The client node will run off and take this next job. And it will keep doing this. And obviously now your speed up is like huge just on these systems. So I talked a lot about this weighting model. So as I said, there's a calibration phase of quantum computing. We calibrate it to some performance statistics. These performance statistics are all probabilistic events. So we kind of give the notion that you can transpile and get this probability of having a correct induction based on all these parameters that you attain from this translation. So they're all bounded by 0 and 1. And the first one is the ability to hold on to information, state decay. The second one is the ability to do operations locally on single qubits. Third one is dual gate fidelity, which is the ability to entangle and create that quantum teleportation. And finally, state preparation and measurement error, which is how likely you are to correctly observe what it actually is. And the great thing about this function is it's so naturally incorporates transpilation in that when you move your circuit to ideal system, the G1 and G2 factors change. And that compensates for suddenly all this diverse, massive suite of current processes that we have today. And so we prove it on a couple of algorithms, a strong, I'm running out of time, so there's a strong linear correlation between our system and actually also observing errors. We proved it on, I think it was around 2,000 circuits we evaluated on X terabytes. And this is the ranking page where just kind of gets a little lost, but all it's saying is if you have a 0.5 performing processor and a 0.2, your 0.5 is going to be scaled to the highest value and your 0.2 to the lowest, and anywhere in between will be linearly scaled between the two. And the max and min weight is according to you. So you might set that balance with 1.5, 0.5 to 1.5, or etc. So let's get into the results. So we did approximately 500,000 circuit evaluations on IBM. This is one of the largest, actually, I believe, evaluations on real quantum computers. These are all real results. None of this is only one rock simulation. This is a sample problem for quantum magnetism, where our Hamiltonian, so it's going to be a 16 by 16 matrix, is defined at the bottom left, where we have these X, Y's, and Z's. These are just 2 by 2 matrices. You don't have to worry about it, it's a little lost, but it's a 16 by 16 matrix that we're trying to optimize. We're trying to find the minimum eigenvalue. And this is from an IBM paper in Nature where they demonstrate efficient hardware ansatz. And we take their problem and we want to work on it. We want to show that we work with it too. So we only connect to IBM. There are a couple systems we connect to, Manhattan, Manila, Goldtown. So these are the ones the client nodes are connecting to. There's 10 of them. So now let's get on to the final results. So let's process this graph one by one. On the left, we have energy, which is kind of our cost, which we're trying to minimize. On the x-axis, epoch. Epoch is the iteration that we are on. The black line, the brown energy, is the energy observed by IBM in their paper. The blue line is the simulator, so that's ideal. That's the only simulation results in this entire paper. That is, if you have a noiseless quantum simulator, you find these results. And then all the other lines, the green line is IBM Q-X2, it's a 5-qubit system. And we observe here, if we look at this graph, IBM Q-X2 actually converges really slowly. But then if you look at the speed graph, IBM Q-X2 has the shortest Q and hence the highest throughput. So suddenly we got this problem of, oh, it's got the shortest Q, let me use it, but also has really bad, not bad, the worst performance of the group. However, then you look at the fastest converting line, which is Casablanca, the purple line, and this is gonna, Casablanca is the fastest converged. So in that training period, it was the best. However, you notice that it starts to increase in energy after around epoch 120. And that's an example of that temporal drift I was talking about. How suddenly your system is degraded in performance, the days, it's getting old. And we need a way for recalibration for it to kind of shoot down. And that happens around epoch 220 in the morning. But you want to mitigate that. These parameters are specific to these machines. And so EQC, the orange line, the shading is standard deviation on runs. We ran it 3 times over 3 days. And we can see that it's pretty stable. This is unweighted notably, so this is just kind of making that ensemble. Converges stably down to the ground energy and exhibits no signs of temporal drift. And the rate at which it converges is like the ensemble, and the performance with speed is so much greater than any of the other independent machines. So finally, looking at if we apply our weighting system, we find that applying our weighting system by applying our smart system management, we're able to convert our systems at a lower energy. We do note that when you have too large of a weighting system and you're kind of putting the weights too high, like 1.75, as you can see, it increases the energy, and this is similar to the analogous problem with classical machine learning of too high of running rates. So, but we do notice that when we apply modest learning rates and we do the system management, we convert at lower eigenvalues, improving system performance and kind of allowing worse machines to contribute computation, but then allow much better machines to kind of drive our energy lower. We also evaluate on QAOA. This is just to kind of show that our system is more generic and can be applied to any variation of quantum algorithm. QAOA is quantum processing optimization algorithm. It generates the same Hamiltonian as a 16 by 16 vector. It's going to be different though. And just, I don't run out of time, so I'm going to give 2 points on this slide. Y-axis is cost, x-axis is iteration. Same as last time, we want to minimize those things. We noticed that all of these systems converge, and in this subgraph in the center, if you look, to the right is better average performance. And we see that an unweighted system having 2 parameters and 10 quantum processes actually was pretty stochastic and pretty random. It converged, but it was at the bottom of the group. But then by applying our weighted system, we were able to boost these performances in these ranking scheme. We were able to boost it up to the 3rd best quantum processor of the ensemble. That's like good. So the impact you can see, 10 seconds. So one, it provides a tremendous amount of power to the researcher and the scientists. It is a lot of ability to train variational algorithms in much shorter periods of time. Not much shorter periods of time. Previously, they were just unattainable. Not unattainable, but just like obviously prohibitive. And sometimes your machine will go offline a week later and you lose your results. Secondly, is one of the pioneering works in distributed quantum computing. Distributed quantum computing is blowing up right now and is growing tremendously. There are inter-fridge links being developed. We are looking at quantum computers that can be connected, from distances using microwave to optical converters. This is an early work in that scene. And finally, it provides this notion of virtualizing quantum computers. No longer really going, I want to use IBM Q Lima, but instead just saying, I want to use IBM Q. And the notion where I don't need to think about which processor is best right now, which processor best suits my circuits. Oh, it's this time of day, it's about to benchmark. You have this high-level ranking system that's a function of your circuit and your system that can kind of say, no, don't go with this really high quantum volume partial system. You have this one right there that actually fits your system really well. And that notion is really powerful. And that's my phone. Thank you.
Thank you.
Cool.
One question, and we'll have to.
Hi, my name is Govind from the University of Chicago as well. So there's an I think you didn't talk about it a lot about like how you actually distribute the tasks over different machines. So for example, like take DQE, what you're doing is you're distributing different polytoms on the different machines, right? So I'm actually concerned if that can be detrimental for convergence because, so it's a simple example, say you're undergoing as just 2 polytoms, okay, and you distribute, well, you put 1 polytom to each machine.
Yeah.
Okay, so I assume that on one of those machines, you have to over-rotate to compensate for error, on the other machine you have to under-rotate to compensate for error.
Yeah.
Now, things you can't do both at the same time because it's the same answers which you are optimizing.
Same with lots of big X-ray.
So what I'm saying is that it's the same parameters which you're optimizing because it's the same answer circuit. So you can, by having an ensemble, you can only correct your parameters to the average noise and not the noise of a particular device. On the other hand, say you had put both those polytoms on one device, you would have the whole correction would have solved the problem because you're producing on one device. So I'm wondering if the fact that you have multiple machines, but the parameters you're optimizing are the same, is actually bad for convergence because the noise can be very different on each.
So, to reiterate your question to make sure I understand correctly, when you're optimizing Hamiltonians, you have this own power strings comprised of, up to 10 million that we need to optimize over, right? And the problem is you might have system 1, system 2, and you're training this VQA over it, and you're going to converge to this minimum eigenvalue. You're saying that we'd rather have one system that is going to learn the noise model than this ensemble, which is going to kind of wash away and not allow it to actually push it lower, right?
Or I'm just saying that you can have the noise in the machines can be pretty different, which means that your answers, parameters are unable to adjust for both of them because it's the same answers, right? Which you have to adjust for the noise.
Yeah. So I think what you're saying is that it's not able to learn the bias of the machine. Like,
right, because of the
yeah, because it's multiple machines. So on that, so the first thing is one, the differentiation is happening on each machine independently. We're running 2 circuits per machine, so it's not in a case where you're trying to do F theta plus delta, F theta minus delta. You're not going to have this. It's the same noise model applied to those 2 functions. So that is mitigated in that sort of regard. And in the second regard, when you're training a Hamiltonian on one system, right? And this is one of the critiques that like a lot of people talk about. Is like you're training on one system, so you once you've got your eigenvalue, you're done, right? But how long does it take you to get your eigenvalue, right? Sometimes your machine decays, your parameters are constantly losing relevance. And with what happens when you have this kind of like ensemble system is you do wash away those bias. And maybe in brief moments you dip lower, but there's no way to actually get the notion of trusting that results. And the use of having this ensemble kind of just allows you to have generalized system management, generalized system parameters that you can reintroduce later. And it's more specific to things such as quantum machine learning, but you do have a desire to reintroduce algorithms. And with Hamiltonians, in the case where you are shooting completely on one system and assuming that noise model remains consistent through that entire time, then you might observe that if you see, if you see the whole point of washing away this bias is you go closer to generalized minimus. And this era algorithms, specifically variational quantum algorithms, are touted to be most resilient. However, in experiments, you do observe that they kind of like shoot up and they don't necessarily converge completely. And having
we have to stop here, so maybe you can think.
Yeah, it's an optimal. Okay.
Next session. So thanks to all the speakers. Session is closed.